Hey guys, Mr. Hendrick here to talk to you about piecewise function in our new unit. And piecewise functions are just combinations of different things that we've seen so far into one function. Think of it like a puzzle and how a puzzle has different pieces that you put together. That's what a piecewise function is going to be. You have left sides of a graph and right sides of a graph and middles of graphs. Okay, we're going to have different pieces fit in different parts of our graph, and that's going to be restricted by only allowing parts to show up on the left side, or only allow parts to show up on the right side, or parts in the middle. We're going to see how this all fits together, as well as a real-world context for these types of problems shortly. So we'll get to graphs in a minute. What I do want to mention is that for piecewise functions, a lot of what we're going to see involves greater than, or less than, or greater than or equal to, or less than or equal to symbols. So if you need some refresher on what those mean, those would be the symbols that you use. And whenever we use these symbols, what we're going to see on a graph is either a hole or a solid dot at the edges of our puzzle pieces, at the edges of our graphs. Okay? If we have a graph that has a piece with a greater than or a less than symbol, that's going to end with a hole. So we'll see what that looks like in a minute. And if we have something that has a greater than or equal to or less than or equal to symbol, where you have that solid line, okay, that's going to be a solid dot on the graph at the edge of our puzzle piece where appropriate. But before I get to the graph, I do want to mention just how piecewise functions might show up in the real world. So this would be a word type problem of a piecewise function that you're creating based on this scenario where you have a post office, right? And depending on how much packages weigh, it might cost you different money to try to ship a package somewhere, right? So for example, let's say that it costs $3 for packages that weigh less than 5 ounces to ship somewhere. So it weighs 4.8 ounces. Okay, that only costs you $3 to ship it. If it weighs 2 ounces, still only costs you $3 to ship. But if it weighs more than 5 ounces, okay, so not 5 ounces itself, 5 ounces can be $3, but more than that, 5.001 ounces, okay, that now costs $5.50 to ship, and all the way up, but below or less than 10 ounces. So 9.99 ounces or 5.001, anywhere in between those, or numbers that are greater than 5 and less than 10. Okay, that's $5.50 to ship those packages. And anything that's greater than or equal to 10 ounces, so 10 ounces, 10.1, 11, 1,000 ounces, $7 to ship it somewhere. So this is just one function, right? You're paying money in any case that you're shipping a package, but there's 3 different scenarios that we have here. We have a $3 scenario, a $5.50 scenario, and a $7 scenario. And that's all according to what the package weighs. So these are your restrictions here, right? Anything less than 5 ounces, and actually what we can say is if we're shipping a package, it has to weigh something. So you could say it has to weigh more than 0 ounces. You can't ship air. Okay, so something between 0, greater than 0, but less than or equal to 5. Okay, that is going to cost $3 to ship. Anything that is between or greater than 5, but less than 10, okay, in between those two values, that's going to cost $5.50. And anything greater than or equal to 10 ounces, that's going to cost you $7 to ship. So this is how you could use a piecewise function. It's all the same function, there's just different pieces that you could put together for this type of problem, and that you could graph, as we're going to see now. So turning to graphs, let's take a look at an example before we try some on our own. That's already been set up. Okay. So we have the definition of a piecewise function. We have 3 different pieces here, a green piece, a red, and a blue. Okay. And these are all going to be different sections of our graph depending on where they're allowed to show up. So for this first piece, for example, okay, if y equals -1, that's like a straight horizontal line at -1, that's allowed to show up anywhere to the left of 0, left of the y-axis, okay? If you graphed this, and use these restrictions anywhere less than 0 along the x-axis, right? If x is negative 0.1 or negative 3 or negative 5 or negative, infinity way over here, okay? X is less than 0, y then is negative 1, right? Right below the x-axis at negative 1. Now notice, we have a hole here. Why do we have a hole? Because there's no solid line underneath this, okay? We're going to be using a hole in this case. Because when x equals 0, this does not apply anymore. If x equals 0, we're not talking about negative numbers, right? We're talking about 0. And when x is 0, we move on to the blue piece, okay? At least in this scenario. So in the blue piece, we have a cube root function, cube root of x minus 2. So think about what the shape of a cube root is. It's like an S, right? And the center of that S will be at 2 units right, okay? We've changed h, we've subtracted next to x. We're transforming a cube root graph to the right by 2 units. So you can see that we have a center of an S here. But that S shape is only going to show up, what we're saying, is it's only going to show up between 0 and 3. Now one of these will have a hole and one will be a solid line. So we have to know which one is which. Remember, anything that has a solid line underneath, so on top of 0 we'll have a solid line, okay, for a greater than or equal to or less than or equal to symbol. And 3, okay, that's language where we have a number that's less than 3, right? That's a hole. Okay, we're talking about less than, not on top of 3, not equal to 3. Okay? If our graph equals 3, or if our function equals 3, if that x value is 3, we're going to move on to the red graph. Okay, that's where it's allowed to be equal to 3, in this case. Now sometimes the graph is never allowed to equal 3. It just depends on your scenario. Here, the red piece is allowed to be greater than or equal to 3 everywhere to the right side of the page towards positive numbers, right? 4, 5, 6. These are all x values to the right that are greater than 3. And what we'll have in this case is an absolute value piece, right? Absolute value functions, like we said before, are shapes of v's. Now the starting point of your vertex, right, the bottom of the v basically, is going to be 4 units right and 1 units down. So 4 comma negative 1 is that bottom vertex of your v. And that v extends up and to the right forever because, again, the graph, that piece is allowed to show up everywhere greater than 3. Okay? But it's not allowed to show up everywhere to the left side of the page because we're stopping at x equals 3. That's why we have a solid line and stop. Okay? Because that's what 1, 2, 3 units over. So all the pieces kind of fit together. So you have 3 pieces, and that's how we would graph them. Okay. So let's take a look at a couple of other examples here. Maybe one more graph before we move on to our last type of function. So let's say that we started with this given, right? Our piecewise function given to us, and now we're expected to be able to graph this. What would we do? Okay. Well, first of all, we have one piece that is going to be a square root. We know that a square root is shaped like a jump. We just have to find out where are we starting. Okay. So we're starting 3 units down, right? That's one of our transformations. And notice this is going to be a hole. Okay. So I'm going to go ahead and try to put something here, 3 units down. I can always erase this. So let's just see what this graph looks like and then where it will and won't show up. Now normally a jump goes up and to the right. Now in this case though it's going to go up and to the left because we have a y-axis reflection, right? So we move 3 units down, but we also flip the jump towards the left side of the page. So normally what this graph might look like would be something like this. Okay. But in this case, notice, the graph can only show up to the left side of the page, okay? Left of -1. So this section right here does not actually exist. It has to be a hole, right? A hole because we're dealing with a less than symbol. And it's less than x equals -1, right? This is Looks like -1, -2. Okay. That's the start of our jump. The jump is going in reverse. And it's not appearing anywhere over here because it's restricted. We have a restriction to the left side of our page. Second piece that we'll have is a exponential function, right? 2 to the power of x minus 2 minus 1. Okay, so this would look like growth. And the asymptote for this would be at -1, so we would normally be able to create a dotted line, -1, graph this like normal. Not in this case. In this case, we will have a restriction between -1 and 4. So I believe that's going to be 4 minus 2. Okay, what we can do here actually, this might be useful. Maybe not. Yep, it's going to show up everywhere a little bit above your asymptote, a little bit above that horizontal dotted line you could create. And when x is 4, 4 minus 2 is 2, 2 squared, or 2 to the second power is 4, and 4 minus 1 is 3. So when x is 4, y is 3. This would normally be what our function would look like. Now, of course, we have to have a hole here as well, right? This second symbol is a less than symbol. That should be a hole. The first symbol is a solid line underneath. Should be a solid dot here. Okay. And let me just confirm that's correct. Yes, it is. The last one now we should have, our last piece down here, is anything that's greater than or equal to 4, anything towards the right side of this page, towards positive infinity along the x-axis. Okay? And this shape of a graph will be a V again because it's an absolute value. Now it's going to be an upside down V in this case. And where that starts is 5 units right, 1 unit up. So that would be 1, 2, 3, 4, 5, 1 unit up. That's our vertex of our V that will be upside down, right? It's flipped over the x-axis or reflected. And so start making a V. Now normally a V would look like this, and you keep going. You're going to keep going one way, okay? You don't have any restrictions over that way. It can be always greater than 4. But in this case, you can't go any numbers less than 4. Now you can equal 4. In this case, it's a solid dot, right? But it can't be anything less than 4. It can't be 3.99. That would take us back to our exponential function. That's how you would graph a piecewise function, one piece at a time. Make sure it fits the appropriate place on the graph. Everywhere left of -1 is your first piece. Anything between -1 and 4 is your second piece. Anything to the right side of the page after or equal to 4 would be your final piece. Make sure also that you're aware of which ones have solid dots, okay, for your greater than or equal to or less than or equal to symbols, versus your holes, where you have a less than symbol or another less than symbol or greater than symbol. But that should help you when you're trying to graph piecewise functions. One more thing I want to cover today. Our final piece of the puzzle for this video, if I may, is what happens when you have a piecewise function that looks kind of like this. So you still have 3 pieces, but now there's no less than or equal to or greater than or equal to symbols. What does this mean? Well, it still has restrictions, right? One piece is a exponential function, and it's allowed to exist when x equals 4. Can it exist when x equals 5? No. That would be actually this piece down here. This piece, right, exists when x equals 5. Does it exist when x equals 6? No. Does this one exist when x equals 6? No. Anything besides a 4 or a 5 will be this bottom piece. Okay, so if you're graphing, think of it like this will give you one coordinate point, this will give you another coordinate point, and the graph down here, this piece down here, will give you everything else. And maybe we'll be able to graph this at the end. But let's try to find specific coordinate points for this function. Okay, so let's find out what does this function equal when x is 4. Now when x is 4, right, g of 4 is x equals 4. G of 4 is going to equal this top piece when a 4 has been plugged into it, right? Because down here, x is not allowed to be 4. And here, x is only allowed to be a 5. This is the piece when x is allowed to be a 4. So that would give us 2 to the power of 4 minus 1 as our exponent, which is 2 cubed. And 2 times 2 times 2 is 8. In other words, a coordinate point of our graph that we could create would be here, 4, 8. Okay. When x equals 4, y has to equal 8 is what this means. Another coordinate point that we could find would be when x equals 5. When x equals 5, what does that mean? We're going to use our second piece, right? That's when x is allowed to be 5, not for the other two. Okay. So when x equals 5, we're going to use the cube root. And that's going to be a cube root of 5 plus 3. We're replacing x with a 5. That's a cube root of 8, which is 2. In other words, when x equals 5, y equals 2. This will be another coordinate point on our graph. Okay. Finally, where we would have our last one, what happens when g is negative 3? X is negative 3 for this function, g of x. When x is negative 3, the only piece that we can use is this bottom one. Okay. This only applies for one value. This only applies for one value. Any other number that you want to test or plug in has to be with this bottom piece. What happens when x is 0? Use this piece. What happens when x is positive 1? Use this bottom piece. You only use the top two, in this case, when they equal those specific numbers. So negative 3, plug into x. Now remember that an absolute value will turn this into a positive. So that's going to be negative positive 3 plus 8. Okay, we still had a negative out in front. That turns it into a negative. Negative 3 plus 8 is 5. In other words, when we have x equal to negative 3, we'll have a coordinate point at 1, 2, 3, 4, 5 here. And if we wanted to create the whole graph, that's not what we're doing or not what we're asked to do in this problem, but if we wanted to create a whole graph, it might look something like this. And then the graph does not exist, this bottom piece graph does not exist here or here. Okay. Something like that. The bottom piece will skip over 4 and 5. Where do those coordinate points show up? They show up for your other two pieces. So we're going to definitely be hitting this pretty hard over the next couple of lessons because it is probably one of the more complex or requires you to have the most grasp or mastery of all of the rest of the units that we've had so far on absolute values and exponents and logarithms and radicals. So we're kind of piecing everything together, and I hope this video helped you in that regard, and I'll see you back to be with you to practice some more.